You are standing on a rock that has been through things no human mind was built to fully comprehend. The ground beneath you has been melted, frozen, smashed, flooded, buried, cracked open, and rebuilt from scratch more times than any scientist can count with complete certainty. The air you are breathing right now was not always there. The oceans were not always there. The continents were not always where they sit today. And life, the thing that makes this planet worth talking about in the first place, almost did not make it more than once. In fact, there were moments in this planet's story where everything came within inches of being erased permanently. Not just human life, not just complex life, all of it. Every bacterium, every fungus, every microscopic organism clinging to the underside of a rock in the ocean, almost gone, forever. And yet here we are, 8 billion people on a rock hurtling through space, most of us completely unaware of the impossible, violent, beautiful chain of events that had to happen in exactly the right order just to make this moment possible. That is the story we are telling today. The full story of Earth. From the very first second of its existence all the way to right now. And I want to be upfront with you before we begin. This story is not short. It cannot be short, because when you are covering 4.5 billion years of history, anything less than the full treatment is a disservice to how extraordinary this planet's story actually is. We are going to go deep. We are going to cover every major chapter: the formation of the solar system, the birth of the moon, the first oceans, the first life, the great extinctions, the age of dinosaurs, the rise of mammals, the emergence of humans, the development of civilization, and where we stand today at what may be another one of those pivotal turning points in Earth's long history. Every single piece of this story connects to the next. Every catastrophe led to something new. Every extinction made room for something that could not have existed otherwise. So if you want to understand why the world is the way it is, not just politically or historically, but physically, geologically, biologically, you have to go all the way back, all the way to the beginning. And the beginning is not on Earth. The beginning is in the dark. About 4.5 billion years ago, there was nothing where our solar system now exists. No sun, no planets, no Earth, no moon, no asteroids drifting through the void. Just a massive, cold, slow-moving cloud of gas and dust drifting through the outer arm of the Milky Way galaxy. Interstellar material, the leftover remnants of older stars that had already lived out their entire lives, burned through their fuel, swelled into red giants, and exploded in supernovae long before our story even began. Everything in that cloud, every atom of hydrogen, every grain of dust, every trace element, had been forged inside the cores of those ancient dead stars. Which means that every atom in your body, every atom in the ground beneath your feet, every atom in every mountain and ocean and living thing on this planet, was created inside a star, was born in stellar fire, scattered across space in a stellar explosion, drifted through the darkness for millions of years as cold interstellar dust, and eventually found its way into the cloud that would become our solar system. You are quite literally made of stardust. That is not a metaphor. That is chemistry. For a very long time, that cloud just existed. Quietly, peacefully, going nowhere in particular. Just drifting through the galaxy in the dark, cold and diffuse and unimpressive looking from the outside. But space is not as calm as it appears, and gravity is the most patient force in the universe. It does not rush, it does not tire, it does not need anything from the process. It simply pulls, constantly, relentlessly, in every direction, drawing matter toward other matter at a rate so slow it would be invisible to any observer watching in real time. And over millions of years, the cloud began to respond. Some event, possibly the shockwave from a nearby supernova, possibly just the slow accumulation of gravitational instabilities within the cloud itself, caused it to begin collapsing. And as it collapsed, it began to spin. The spinning was slow at first, but like a figure skater pulling their arms inward to rotate faster. As the cloud contracted, its rotation accelerated, it flattened into a disk, a vast spinning disk of gas and dust with a dense, hot, rapidly growing mass at its center. That central mass grew more dense, more hot, and more compressed with every passing year as more material rained down onto it. The pressure inside it became unimaginable, and then, at some point, at some threshold of temperature and pressure that physics demanded be crossed, something happened that had never happened in that particular region of space before. Hydrogen atoms, stripped of their electrons by the extreme temperature, began colliding with enough force to fuse together and form helium. Nuclear fusion ignited. The energy released was staggering. A shockwave of heat and radiation blasted outward from the center of the disk, halting the infall of more material. And the region that had been dark for billions of years was suddenly, brilliantly, overwhelmingly lit. Our sun had turned on for the very first time. A brand new star, yellow, stable, pouring out light and heat in every direction, and the leftover material in the disk surrounding it, all the gas and dust and rock and ice that had not made it into the star itself, that material was now on its own, spinning around the new sun, slowly cooling, slowly clumping together under the influence of gravity. The planets were beginning to form, and one of them, the third clump of rocky material from the sun in the region where temperatures were warm enough for liquid water to someday exist on the surface, was Earth. The early solar system was a violent, chaotic place in a way that is hard to overstate. The orbits of the young planets had not yet settled into the stable, predictable paths they follow today. Large objects were crossing each other's orbits constantly. Collisions were not occasional events. They were the defining feature of the environment. Every planet in the solar system bears the scars of this period. The craters you see on the Moon, on Mars, on Mercury, those are the records of a time when the inner solar system was essentially a shooting gallery, and everything that existed was constantly being hit by everything else. Early Earth was no different. It was hot, molten, relentlessly bombarded. Its surface was a sea of liquid rock punctuated by massive impact craters as asteroids and comets slammed into it from every direction. There was no crust, no oceans, no atmosphere worth speaking of, just a ball of molten rock being continuously pounded in the dark. And then came the hit that changed everything. At some point in those first tens of millions of years of Earth's existence, an object approximately the size of Mars was on a direct collision course with our young planet. Scientists call this object Theia. The name comes from Greek mythology. Theia was the mother of Selene, the goddess of the moon. And the reason the name was chosen with that particular symbolism will become clear in a moment. Theia did not brush past Earth. It did not create a near miss. Theia hit Earth directly, with a force so incomprehensibly enormous that there really are no adequate human-scale comparisons to offer. The entire surface of Earth was vaporized in an instant. Both objects, both planets, were partially destroyed by the impact. The cores of the two worlds merged, sinking toward the center of the combined mass, and an enormous quantity of material from both planets was thrown outward, blasted into orbit around what remained of Earth in a ring of vapor and debris and molten rock. But gravity once again did its patient work. Over time, the material in that debris ring began sticking together. Clumps formed. Clumps attracted more material. Gradually, the ring of debris coalesced into a single spherical body in orbit around Earth, the Moon, formed from the destroyed remains of two planets smashed together at the dawn of the solar system. The Moon settled into orbit at a distance that would, hundreds of millions of years later, produce tides in Earth's oceans powerful enough to be one of the factors that helped life emerge and diversify. The Moon stabilizes Earth's axial tilt, preventing the wild swings in the planet's orientation that would produce catastrophic climate extremes. The Moon controls our tidal rhythms, which shape the evolution of countless marine and coastal species. The Moon is not a coincidence or a backdrop detail in Earth's story. It is one of the central characters, and it was born from catastrophe. In the aftermath of the Theia impact, Earth slowly pulled itself back together. The merged cores settled. The surface gradually solidified as the planet lost heat to space over millions of years. And as it cooled, gases trapped in the rock were released, a process called outgassing, filling the space around the planet with the beginnings of an atmosphere. This first atmosphere was nothing like what we breathe today. It was a thick, toxic mixture of water vapor, carbon dioxide, methane, hydrogen sulfide, and nitrogen. No free oxygen, no breathable air, just a dense, hot, poisonous envelope of gas surrounding a still hot, still geologically violent world. Volcanoes erupted constantly across the surface, adding more gases to the atmosphere, more material to the surface. The young Earth was volcanically active in a way that makes modern volcanic activity look trivial by comparison. Essentially, the entire surface was geologically restless, heat pouring out of the interior in a global volcanic event that lasted for millions of years. And then, as the planet continued to cool, something crucial happened with all that water vapor in the atmosphere. It rained. The atmosphere, cooling as the planet lost heat to space, could no longer hold all the water vapor it contained, and it began to condense and fall. Not a brief shower, not a season of rain. an almost incomprehensibly long period of rainfall that lasted millions of years. Rain falling onto a hot, barren, rocky surface, flowing into the low points of the landscape, pooling, deepening. Around 3.8 billion years ago, the process was complete enough that Earth had its first oceans. Not the oceans we know today, they were shallower, hotter, chemically different, covering far more of the surface than today's oceans do because there was very little dry land. But they were oceans, liquid water on the surface of a rocky planet. And with liquid water, the chemistry of life became possible. The exact mechanism by which the first life appeared on Earth is one of the most actively researched questions in all of science, and we do not yet have a definitive answer. What we do know is that it happened approximately 3.7 billion years ago, give or take. Something that meets the definition of life existed in the early oceans, microscopic, single-celled, with no nucleus, no complex internal structures, no eyes or legs or any of the features we associate with living things when we think of the world around us today. Just tiny, self-replicating chemical systems enclosed in a membrane, capable of consuming energy and making copies of themselves. The most primitive possible version of what it means to be alive, but alive. Genuinely, biologically alive. What is perhaps most astonishing about the appearance of life is not that it happened, as extraordinary as that is, but how quickly it happened after the conditions that could support it were in place. The window between when Earth's surface cooled enough for liquid water to exist stably and when the first evidence of life appears in the geological record is not hundreds of millions of years, it is tens of millions of years. On a geological timescale, the emergence of life was almost immediate once the planet was ready for it. This suggests, though does not prove, that life is not an almost impossibly unlikely accident, but rather the predictable chemical consequence of the right conditions being in place. It suggests that wherever in the universe those conditions exist, liquid water, energy sources, the right chemical building blocks, life may emerge. That is an idea with staggering implications for how we think about our place in the universe. For the next several 100 million years, that early life did not do anything particularly dramatic by the standards of what was coming later. Those early microbes lived in the oceans, consumed whatever chemical energy was available to them, and they reproduced. Generation after generation, billions of individuals, each one slightly different from its parent due to the inevitable errors in copying genetic information, each slightly different version of the organism competing with all the others for the available resources. This is evolution by natural selection. The organisms best suited to their environment survive and reproduce more successfully. Their traits become more common. Over time, populations change. Species change, and over very long time periods, entirely new forms of life emerge from the accumulation of many small changes. It is a process of no particular intelligence or direction, driven by nothing more than the cold logic of which variants survive to reproduce, and which do not. And yet from that simple mechanical process, over billions of years came every living thing that has ever existed on this planet. Around 3.3 billion years ago, something was happening beneath the surface of the planet that would begin to reshape the face of Earth. The geological processes driven by the enormous heat of the Earth's interior were pushing material upward through the crust in certain locations. Heat plumes rose from deep within the mantle and pushed against the underside of the crust, lifting it, thickening it, causing it to rise above the surface of the surrounding ocean in some places. The very first land was emerging, not dramatic mountain ranges or wide continents, just scattered low-lying rocky platforms poking above the ocean surface. Scientists call the earliest stable pieces of continental crust cratons, and the first known grouping of them into something resembling a landmass is called Valbara. It was small, significantly smaller than modern Australia. Rocky, barren, lifeless above the waterline because life had not yet figured out how to live on land. But it was there, solid ground above the ocean, the foundation of a process of continental growth that would continue for the next 3 billion years. Back in the oceans, the microscopic life was slowly diversifying, and around 2.4 billion years ago, one group made a discovery that would be the most consequential biological innovation in the history of the planet. More consequential than the development of the nucleus, more consequential than the emergence of multicellular life, more consequential than the evolution of intelligence. A group of single-celled organisms we now call cyanobacteria evolved the ability to use sunlight as their primary energy source. They could capture photons of light from the sun and use that energy to drive chemical reactions that converted water and carbon dioxide into sugar, with a byproduct that was simply released into the surrounding water and eventually into the atmosphere. That byproduct was oxygen, photosynthesis, the ability to feed off sunlight. Today it seems like the most natural thing in the world. Plants do it everywhere. It powers most of the food chains on Earth. But 2.4 billion years ago, it was a revolution, a biological revolution that would change the chemistry of the entire planet. Because when you have trillions upon trillions of cyanobacteria in the ocean, all of them releasing oxygen as a waste product of their metabolism, you are pumping an enormous amount of a highly reactive gas into the environment every single day. And that oxygen began to accumulate, slowly at first. Much of it reacted with iron dissolved in the oceans, which is why there are banded iron formations in rocks of this age around the world. The geological fingerprint of all that oxygen reacting with iron and settling to the seafloor. But eventually the iron was used up, and the oxygen had nowhere to go but up, into the atmosphere. The Great Oxidation Event, as it is called, began around 2.4 billion years ago and unfolded over millions of years. And it was simultaneously the best and worst thing that had ever happened on Earth, depending on which organisms you were asking. For the forms of life that had evolved in an oxygen-free environment, which was essentially all life on Earth at that point, free oxygen was toxic, lethal. Oxygen is highly chemically reactive, and for organisms whose biology had evolved without it, exposure to significant amounts of it was devastating. The Great Oxidation Event triggered one of the largest mass extinctions in the history of life on Earth. The vast majority of the microbial life that had populated the early oceans could not survive the new oxygen-rich environment. The organisms that could adapt did. The ones that could not found refuge in environments where oxygen could not reach, deep in the sediment, around hydrothermal vents, in anaerobic pockets scattered across the ocean floor. Some of their descendants still live in those kinds of environments today, as unchanged in their fundamental biology as they were billions of years ago. But the dominant story of life on Earth after the Great Oxidation Event belonged to the organisms that not only tolerated oxygen, but learned to use it. Because oxygen, for the organisms that can use it, is an extraordinarily powerful energy source. Aerobic respiration, the process of burning food with oxygen, releases far more energy than any anaerobic process. The organisms that mastered aerobic respiration could be bigger, more active, more complex. The stage was being set, slowly and over hundreds of millions of years, for the eventual emergence of complex animal life. But first, a consequence of the Great Oxidation Event that is worth understanding fully. All that new oxygen in the atmosphere dramatically reduced the concentrations of methane and carbon dioxide, two powerful greenhouse gases that had been doing an important job of keeping the planet warm. Remove the greenhouse gases, and the planet loses heat rapidly. Around 2.4 billion years ago, Earth experienced its first major global glaciation, an ice age so severe that ice sheets may have extended all the way from the poles to the equator. Scientists call this the Huronian glaciation, and it was not a brief cold snap. It lasted tens of millions of years. The planet essentially froze solid. Life did not go extinct. The organisms that had adapted to oxygen found ways to survive even in this drastically cold environment, huddled in whatever warm, ice-free refuges remained. But the world had become a very different, very hostile place. Frozen, silent, white, a planet that, from space, would have looked nothing like the blue marble we know today. Eventually, volcanic activity pumped enough carbon dioxide back into the atmosphere over millions of years to warm things back up again. The ice retreated, and life, which had spent tens of millions of years enduring the cold, began expanding and diversifying once more into a world that was now, for the first time, genuinely oxygen-rich. Now we need to spend some time with the continents, because understanding what the continents were doing throughout all of this is essential to understanding how the planet's story unfolded. The concept of plate tectonics, the idea that Earth's surface is divided into large plates that move slowly over the surface of the planet, was not accepted by mainstream science until the 1960s. Today it is as well established as the theory of evolution or the germ theory of disease. The evidence is everywhere, from the matching coastlines of South America and Africa to the identical fossils found on continents now separated by thousands of miles of ocean, to the GPS measurements that directly track the movement of tectonic plates in real time. The continents move, always have, and the story of where they have been and where they are going is one of the most dramatic stories in Earth's history. Around 1.1 billion years ago, most of the land on Earth had drifted together into what may have been the largest supercontinent in Earth's history. Scientists call it Rodinia. All, or nearly all, of the continents that exist today were assembled into this one enormous landmass, surrounded by a single vast global ocean. The interior of Rodinia, far from the moderating influence of any coast, would have been brutally dry and harsh. Life, which was still confined entirely to the oceans at this point, would have known nothing of Rodinia except perhaps the chemistry of the rivers that drained off it into the surrounding sea. But the presence of Rodinia was shaping ocean currents, climate patterns, the chemistry of the ocean itself, in ways that affected everything living in that ocean. And then Rodinia began to break apart. Tectonic forces pulled the supercontinent apart along fracture zones, opening new ocean basins, flooding previously dry land, reshuffling the climate patterns of the entire planet. The breakup of Rodinia contributed to another severe global glaciation. Scientists call this one Snowball Earth, and the evidence suggests it may have been even more severe than the Huronian glaciation a billion years earlier. Possibly the entire ocean, from pole to pole, froze over. A thin liquid layer may have persisted beneath the ice in tropical regions, kept liquid by the heat of the sun and geothermal heat from below. And in that thin liquid layer, life survived. It always survived. But Snowball Earth represents another of those almost extinction-level moments in the planet's history, a period when life on Earth was reduced to the most marginal, desperate existence imaginable, clinging to whatever warmth remained in a frozen world. Again, volcanic activity eventually saved the day, pumping enough carbon dioxide into the atmosphere over millions of years to melt the ice. And when the ice finally melted, rapidly, geologically speaking, in a matter of thousands rather than millions of years, the surge of nutrients from the previously frozen land into the warming oceans may have been one of the triggers for what happened next. Because around 540 million years ago, after the long, slow billions of years of microbial life evolving in the background, something happened in the oceans of Earth that was so sudden and so dramatic by geological standards that it stands as one of the most discussed events in all of paleontology: the Cambrian explosion. In a geologically brief window of time, tens of millions of years, which sounds long but is essentially an eye blink on the timescale we have been working with, the diversity of life on Earth exploded. Before the Cambrian period, the fossil record shows us a world of mostly soft-bodied, simple organisms. After the Cambrian, the fossil record explodes with complexity, variety, and recognizability. Animals with shells, animals with eyes, animals with legs and claws and spines and complex body plans, predators and prey, locked in evolutionary arms races that drove the rapid development of defensive and offensive adaptations. The ecological dynamics of the modern world, competition, predation, symbiosis, the food chain, appeared in recognizable form for the first time. The most famous of the Cambrian creatures are the trilobites, hard-shelled, multi-segmented arthropods that came in hundreds of different species, ranging from microscopic to nearly a meter in length, with compound eyes sophisticated enough to rival those of modern insects. Trilobites dominated the oceans for an extraordinary stretch of time. They were abundant and diverse during the Cambrian. They survived the next several 100 million years of Earth's history, and they only finally went extinct in the Great Dying 252 million years ago. They outlasted most of the other Cambrian creatures by hundreds of millions of years. But they were not alone. There were filter feeders anchored to the seafloor, predators like Anomalocaris, a meter-long predator with circular grasping mouthparts and compound eyes, swimming through the Cambrian Ocean as the apex predator of a world that had never seen a top predator before. There were worms and jellyfish and creatures with no living relatives today, body plans that evolution tried once and then apparently abandoned. The Cambrian seas were a world of biological experimentation on a scale that had never existed before. The rulebook of what a living thing could look like was being written for the first time, and for a brief period, almost anything was a viable answer. But then came the first great test of the new complex life that had emerged so explosively in the Cambrian. Around 440 million years ago, roughly 100 million years after the Cambrian explosion, a combination of factors including significant climate change, possibly linked to glaciation at the South Pole, caused global temperatures to drop sharply and ocean chemistry to shift. The result was the Ordovician-Silurian extinction event, the first of the 5 great mass extinctions that would punctuate Earth's history over the next 400 million years. An estimated 85% of all species on Earth went extinct. The extraordinary diversity of the Cambrian and Ordovician oceans was devastated. The trilobites survived, barely, reduced to a fraction of their former diversity. The reef ecosystems that had been so rich and productive in the shallow Ordovician seas were largely destroyed. And yet, as always, life persisted. The survivors repopulated the emptied niches. New forms evolved to replace those that had been lost. The ocean refilled with living things, changed in composition but still rich with life, and the evolutionary story continued. In the long recovery period following the Ordovician Silurian extinction, something was beginning to happen on the edges of the continents that would eventually change everything about the way life worked on Earth. Life was preparing to leave the ocean. The ocean had been the exclusive domain of life for the first 3 billion years of Earth's biological history. The land surface was barren, exposed, alien, baked by ultraviolet radiation that the thin, still developing ozone layer did not yet fully block, with no soil as we know it, no food sources, no shelter. The challenges facing any organism that tried to establish itself on land were enormous, but the rewards for doing so were equally enormous. Vast new habitats with no competition, no predators, abundant sunlight, and slowly, incrementally, life began the transition. Plants were first. Simple, early plants, related to modern mosses and liverworts, began establishing themselves in the zone between the water and the dry land. Somewhere between 470 and 430 million years ago, plants made the transition to fully terrestrial life, evolving the structural support systems needed to grow upright without the buoyancy of water to help, the waterproofing systems needed to prevent desiccation in dry air, and the root systems needed to anchor into the substrate and absorb water from the ground. It was slow going at first, but once plants had a foothold on land, they began their own process of explosion and diversification. Within a relatively short geological time frame, plants had spread across the available land surfaces of the planet. Forests appeared, actual forests, with trees growing taller and taller as they competed with each other for access to sunlight. By about 385 to 350 million years ago, in the Devonian period, Earth had forests that would be recognizable to us today, albeit composed of species that no longer exist. The land was green for the first time in Earth's history, and where plants went, animals followed. The transition of animals from water to land is one of the most studied major evolutionary events in the fossil record. The first land vertebrates evolved from fish, specifically from a group of lobe-finned fish whose strong, fleshy fins contained the same basic bones that would eventually become the legs, arms, and hands of all terrestrial vertebrates, including us. The famous transitional fossil Tiktaalik, discovered in 2004 in Arctic Canada and rocks approximately 375 million years old, shows an animal partway through this transition, a fish with a neck, with a flat head like a crocodile's, with fins whose internal structure shows the beginnings of the wrist bones that would eventually become the wrist in your hand. Tiktaalik could likely prop itself up on its fins and lift its head to look around in the shallow, weedy waters at the edges of Devonian rivers and swamps. It represents one of the most extraordinary moments in the history of life, the moment when life first began the genuine transition from the water to the land. From Tiktaalik and creatures like it, over millions of years of further evolution, came the first amphibians, then the first reptiles, then the dinosaurs, the mammals, and ultimately us. As life was completing its conquest of the land during the Carboniferous and Permian periods, roughly 360 to 252 million years ago, the continents were once again on the move. The separate land masses were slowly colliding with each other again. Mountain ranges rose where the plates met, ocean basins closed. And by around 300 million years ago, essentially all of the land on Earth had assembled once again into a single enormous supercontinent, Pangaea, the last great supercontinent, a massive landmass stretching from pole to pole, surrounded by a single vast ocean called the Panthalassic Ocean. Life on land had by this point become extraordinarily diverse. Forests covered much of the equatorial regions, insects had evolved and diversified into thousands of species. The Carboniferous period had oxygen levels higher than today, and some scientists believe this contributed to the evolution of giant insects, including dragonflies with wingspans of more than 60 centimeters. Early reptiles had evolved and were spreading across the land. The world was warm, relatively stable, and biologically rich in a way it had not been since the Cambrian. And then came the end of everything. 252 million years ago, at the boundary between what geologists call the Permian and Triassic periods, Earth experienced the most devastating mass extinction event in its entire history. The name scientists have given it captures the scale of what happened with appropriate directness: the Great Dying. Whatever the precise combination of causes, and the evidence points most strongly to massive, sustained volcanic activity in what is now Siberia, where enormous quantities of lava flooded an area of land the size of a continent over the course of perhaps 1 million years, releasing staggering amounts of carbon dioxide, sulfur dioxide, and other gases into the atmosphere. The environmental consequences were catastrophic beyond any other event in the fossil record. Global temperatures spiked by perhaps 10 degrees Celsius or more. The oceans warmed dramatically and lost much of their dissolved oxygen. Ocean chemistry changed toward increased acidity. The atmosphere became laden with toxic gases and particulates. Acid rain fell on the forests and the land. The Earth, for perhaps hundreds of thousands of years, became a genuinely hostile place for most forms of life. The losses were staggering. Approximately 96% of all marine species went extinct. Let that number sink in for a moment. 96%. The oceans, which had been teeming with life for hundreds of millions of years, with fish and corals and crinoids and brachiopods and sharks and cephalopods and countless other creatures, were reduced to a biological shadow of what they had been. The reef ecosystems that had been building and diversifying for hundreds of millions of years essentially ceased to exist. On land, roughly 70% of all vertebrate species were lost. The reptiles, insects, amphibians, and early proto-mammal creatures that had been spreading across Pangaea for tens of millions of years were devastated. The forests died back dramatically as the climate shifted. The soil ecosystems were disrupted. The food chains collapsed. The Great Dying was, by any reasonable measure, the worst thing that has ever happened to life on Earth, and it took millions of years for the planet to recover. The early Triassic, the period immediately following the extinction, is sometimes called the dead zone by paleontologists. The fossil record from this period is sparse and impoverished, dominated by only a handful of surviving species that expanded to fill the emptied world. But it did recover. It always does. And into the emptied world of the early Triassic, a group of reptiles that had survived the extinction in modest numbers began to expand with extraordinary speed and versatility. The first dinosaurs appeared somewhere around 230 to 240 million years ago, in a world that was still recovering from the Great Dying. They were not particularly dramatic at first. Small, bipedal reptiles, quick and agile, probably insectivores and small prey hunters. Nothing about those early forms would obviously suggest that their descendants would rule the planet for the next 150 million years. But they had certain advantages: efficient lungs, upright posture that made them more energetically efficient than the sprawling reptiles that competed with them. And as the Triassic world opened up, they diversified. By the end of the Triassic period and the beginning of the Jurassic, roughly 200 million years ago, dinosaurs had become the dominant large land animals on Earth, and they would remain so for the next 150 million years. 150 million years. The number is almost impossible to place in context. Modern humans have existed for perhaps 300,000 years. Our genus Homo has existed for perhaps 2.5 million years. The entire primate order is perhaps 60 million years old. The dinosaurs ruled the land for 150 million years. They had more time to evolve, diversify, and change than we can meaningfully comprehend. And they used every bit of it. From the earliest modest dinosaurs of the late Triassic, the dinosaur lineage produced a range of creatures that staggers the imagination. Long-necked sauropods that grew to lengths of 30 or 40 meters and weights of 70 or 80 tons, the largest land animals in the history of the planet. Armored ankylosaurs with tails modified into bone clubs capable of breaking the legs of any predator foolish enough to approach from behind. Horned ceratopsians living in enormous herds, migrating across the landscapes of late Cretaceous North America in numbers that may have rivaled the bison herds of the 19th century. And the predators, the theropods, ranging from small, feathered, intelligent hunters that looked remarkably bird-like to the enormous apex predators of the late Mesozoic, including Spinosaurus, the largest predatory dinosaur known, and of course Tyrannosaurus rex. The T-Rex deserves more than a passing mention, because it has become such a cultural icon that it has lost some of its power to properly impress us. Tyrannosaurus rex was a 6 to 9 ton biped, with a skull more than 1.5 meters long, arms that were actually powerful enough to lift several hundred pounds, and a bite force that was the strongest of any land animal in the history of the planet. Its teeth were not just for puncturing. They could crush bone completely, allowing it to extract the nutritious marrow that other predators could not access. Recent research on the anatomy of its skull suggests that its senses were extraordinarily acute. Large olfactory bulbs indicate an excellent sense of smell. Large optic nerves suggest vision that was potentially sharper than a modern hawk's, and the structure of its inner ear suggests it was particularly sensitive to low-frequency sounds that carry further through forested environments. The T-Rex was not the slow, lumbering, nearly blind predator that older depictions suggested. It was a sophisticated, highly evolved apex predator, probably warm-blooded to at least some degree, possibly feathered in some parts of its body, and certainly more intelligent than the simple reptile brain model that popular culture has traditionally assigned it. Standing next to a T-Rex in the late Cretaceous would not have been like standing next to an enormous alligator. It would have been like standing next to something that was paying very close attention to you, processing exactly what you were, and deciding what to do about it. All of this, the entire incredible 150-million-year dynasty of the dinosaurs, came to an abrupt and violent end 66 million years ago. An asteroid approximately 10 to 15 kilometers in diameter, moving at something like 20 kilometers per second, entered Earth's atmosphere and slammed into the shallow waters near what is now the Yucatan Peninsula of Mexico. The force of the impact was so incomprehensibly enormous that the rock beneath the impact site was instantly vaporized and blasted outward. A fireball of superheated gas and debris expanded from the impact site at hypersonic speeds. Within minutes, the surrounding region for thousands of kilometers was consumed by fire. Within hours, debris thrown into the upper atmosphere was raining back down around the globe, creating friction as it re-entered and heating the air to temperatures capable of igniting wildfires over wide areas. Within days, the enormous quantity of dust and soot and sulfur compounds blasted into the upper atmosphere had begun to spread around the entire planet, blocking sunlight. Within weeks, global temperatures began to drop as photosynthesis was disrupted across the planet. The food chains that depended on plants began to collapse. The food chains that depended on those food chains collapsed in turn. And the dinosaurs, the enormous, warm-blooded, highly metabolic animals that required vast quantities of food to sustain themselves, began to die. Not immediately. The extinction played out over thousands of years as the global ecosystem collapsed around them. But the outcome was not in doubt once the asteroid had hit. The world that the dinosaurs had ruled for 150 million years no longer existed. The climate that had supported them, the ecosystems that had fed them, all of it was being dismantled by the aftermath of one catastrophic impact. And when the dust finally settled, when the skies cleared and light returned and the survivors began picking through the wreckage, the non-avian dinosaurs were gone. Every species, the most successful, diverse, long-lasting group of large land animals in Earth's history, erased in a geological instant. What was left? The survivors of the asteroid impact were by and large the small things, the things that could hide, the things that could go dormant when food was scarce, the things that could eat seeds or insects or the decaying remains of other organisms. Mammals, which had existed throughout the age of dinosaurs but had been largely confined to small, nocturnal, shrew-like roles by the dominance of the dinosaurs, survived in large numbers. Birds, which are the direct descendants of a lineage of theropod dinosaurs, survived and would go on to diversify enormously. Crocodilians survived, having barely changed from their Mesozoic ancestors to this day, testimony to how well-designed that body plan is for its ecological role. And into the ecological space left behind by the fallen dinosaurs, the mammals began to expand. The diversification of mammals in the Paleogene period, the roughly 40 million years following the asteroid impact, was one of the most rapid adaptive radiations in the history of life on Earth. Within 10 million years of the extinction, mammals had diversified into a remarkable array of forms. The ancestors of whales had entered the ocean. The ancestors of bats had taken to the air. Early horses and rhinoceroses and elephants and deer were diversifying on the land. Early primates had appeared in the trees of the tropical forests, and in those tropical forests, clinging to the branches, eating insects and fruit, the primates quietly began evolving towards something the planet had never produced before. The primate lineage that would lead to humans began in the trees of African forests sometime around 60 million years ago. For tens of millions of years, our ancestors were fully arboreal, tree dwellers, adapted for climbing and grasping, with forward-facing eyes that gave excellent depth perception for judging distances when leaping between branches. This was the period during which the hands that now build cathedrals and perform surgery were being shaped by evolution, not for any of those purposes, but simply for grabbing branches and peeling fruit. The large brains that would eventually compose symphonies and write philosophy were being shaped, not for any of those purposes, but simply for the complex social navigation of living in large primate groups with intricate hierarchies, alliances, and rivalries. Evolution has no foresight. It was building these traits because they helped our ancestors survive in the trees, not because it knew that tens of millions of years later those same traits would be applied to problems it could not have anticipated. About 6 million years ago, in Africa, the environmental conditions were changing. The dense forests that had covered much of the continent were giving way in many areas to more open woodland and savanna environments. And in those more open environments, a new locomotion strategy began to offer advantages. Walking upright on two legs, bipedalism, kept the head elevated above the grass, allowing better scanning for predators and prey. It freed the hands, which could now carry food, tools, and infants while walking. It was an energetically efficient way to cover long distances across open terrain. The earliest members of the human family, species like Sahelanthropus chidensis, found in Chad and dating to about 6 million years ago, show the beginnings of this transition. By about 4 million years ago, the picture becomes clearer. Australopithecus was walking upright on a regular basis. The hip and leg bones of Australopithecus are clearly adapted for bipedal locomotion. The footprints at Laetoli in Tanzania, preserved in volcanic ash dated to about 3.7 million years ago, show distinctly human-like tracks made by at least two individuals walking side by side. These were fully upright walkers, but their brains were still small, roughly a third the size of a modern human brain, and their faces were still strongly ape-like. They were human below the neck and ape-like above it in a sense. They were our ancestors, and they were extraordinary. But they were not yet us. The transformation toward modern humanity picked up speed around 2 to 3 million years ago with the emergence of the genus Homo. The first members of our genus showed something new: deliberate stone tool use. The Oldowan tool industry, named after the Olduvai Gorge in Tanzania where many early examples were found, represents the oldest confirmed human technology. Simple, crude, just a stone flake struck from a larger stone to create a sharp edge, but made with intention, made because the creature who made it had a mental template of what it wanted to create, and the manual dexterity and cognitive planning ability to produce it. Tools change everything. With a sharp stone flake, you can butcher a carcass that your teeth alone could not handle. You can access marrow from bones that other scavengers cannot crack. You can process plant foods that would otherwise be indigestible. Tools expand the range of resources available to the creatures that use them, and that expanded resource base can support larger brains, which in turn leads to more sophisticated tool use, in a positive feedback loop that drove the rapid growth of human cognitive capacity over the next 2 million years. The discovery of fire, or more precisely, the controlled use of fire, is typically placed around 800,000 years ago based on the earliest convincing archaeological evidence. The impact of fire on human evolution is difficult to overstate. Cooking food dramatically increases its digestibility and the caloric value the body can extract from it. Raw meat, raw tubers, raw grains, these are hard to chew and relatively low in the calories that a large, metabolically expensive brain requires. Cooked meat is tender and easy to process. Cooked starchy foods become far more calorie-dense. The shift to cooked food may have allowed the gut to shrink relative to body size, freeing up caloric resources for the brain to grow. The correlation between the appearance of controlled fire in the archaeological record and the rapid increase in cranial capacity in the human fossil record is not coincidental. Fire may have literally built our brains, and beyond the metabolic impact, fire transformed human social life. A fire around which a group gathers in the darkness is a social space unlike anything that existed before. It is a place of safety where predators are kept at bay, a source of warmth that makes cold night sleeping possible, a light source that extends the social day beyond sunset, and a focus for the kind of extended social interaction, conversation, storytelling, the sharing of information that is one of the foundations of human culture. Every human culture in history has had fire. Every human culture has gathered around it. The campfire is as old as modern human cognition, And it is possible that the evolution of language itself was partly shaped and accelerated by the long evenings spent around fires, communicating in the safety and warmth of the light. By about 300,000 years ago, anatomically modern Homo sapiens had appeared in Africa. Brains essentially the same size and structure as ours. Faces essentially like ours. Hands essentially like ours. But the transition to full behavioral modernity, the kind of abstract thinking, symbolic behavior, long-range planning, and technological innovation that defines us most distinctively, appears to have been essentially complete by about 70,000 years ago. Around that time, something changed in human cognition that dramatically accelerated the pace of cultural and technological development. The evidence is in the archaeological record, a sudden appearance of cave art, of personal ornaments, of evidence for long-distance trade networks, of far more sophisticated and varied tool technologies. Whatever changed in the human mind around this period, the result was a species with cognitive capabilities unlike anything that had ever existed before on this planet. And that species began to expand. Out of Africa, populations of modern humans spread into the Middle East, into Europe, into Central and South Asia, eventually into Australia and the Americas. Wherever they went, they brought their cognitive revolution with them, their tools, their social structures, their ability to adapt culturally to new environments far faster than biological evolution could. They encountered other human species as they spread, Neanderthals in Europe and the Middle East, Denisovans in Asia, and the evidence now shows that they did not simply replace these species immediately through competition. They interbred with them. The DNA of most modern humans outside of Africa contains small but measurable percentages of Neanderthal DNA. The DNA of people in some parts of Asia and Oceania contains Denisovan DNA. The story of human origins is not a simple story of one species replacing all others. It is a more complex story of encounters, competition, partial merging, and gradual replacement that played out over thousands of years across multiple continents. But the outcome was the same everywhere. By roughly 40,000 to 15,000 years ago, all human species except Homo sapiens had disappeared. We were the last ones standing. And what did those last remaining humans do with the world they had inherited? They painted it. At Lascaux in France, at Altamira in Spain, at Chauvet, at dozens of other sites around the world, our ancestors painted the walls of caves with images of the animals around them: horses, aurochs, bison, lions, bears, rhinoceroses, with a skill and artistry that still impresses modern observers. These paintings are not crude scrawlings. They are sophisticated representations using perspective and shading and the contours of the cave walls to create three-dimensional effects. They were made by people who were fully, completely, unmistakably like us. Not proto-humans, not transitional forms, but people who saw the world as we see it and felt the need to represent it, to capture something about their experience of being alive in it. The impulse to make art, to communicate across time and space through symbolic representation, is one of the things that makes us most distinctively human, and it is very old. About 10,000 years ago, the pace of human history began to accelerate dramatically. The last ice age was ending, the climate was warming and stabilizing, and in several locations around the world, independently and at roughly similar times, human populations began doing something that none of their ancestors had ever done. They began deliberately cultivating plants and domesticating animals. They began farming. The shift from a nomadic hunter-gatherer lifestyle to a settled agricultural one was not instantaneous. It happened gradually, over thousands of years, as people experimented with managing the wild plants and animals around them and became more dependent on domesticated varieties. But the consequences of this shift were transformative on a scale that rivals any event in the geological record for its impact on the planet. When you can grow your own food in a predictable and reliable way, you do not need to follow it across the landscape. You can stay in one place. You can build permanent structures. You can accumulate possessions. You can support a larger population than a given area of land could support through hunting and gathering alone, because agriculture dramatically increases the caloric output per unit of land. Populations grew, villages appeared, then towns, then cities. Cities required organization. Who owns what? Who owes whom what? How do we resolve disputes? How do we coordinate the construction of infrastructure? Governance appeared, and cities required record-keeping. How much grain is in the storehouse? Who paid their taxes? What did we agree to trade? Writing was invented. And writing, the ability to record information externally, outside the limits of any individual memory, in a form that could be transmitted across time and space, was the technological development that made the accumulation of knowledge across generations possible. Before writing, each generation had to relearn most of what it knew from the previous generation through direct teaching and oral tradition. After writing, knowledge could be stored, retrieved, built upon. Civilization became possible. From the first farming villages of the Neolithic period, the story of human civilization unfolds across several thousand years with an acceleration that only becomes more dramatic as it continues. The first cities appeared in Mesopotamia around 6,000 years ago. Writing appeared in Mesopotamia and Egypt around 5,000 years ago. Mathematics, astronomy, engineering, philosophy, medicine, all of these developed as the accumulated knowledge of civilizations was recorded, transmitted, debated, refined, and built upon. Empires rose and fell. Trade networks spanning thousands of miles connected distant civilizations. Ideas, technologies, crops, and diseases spread along those trade networks. The history of human civilization from the first cities to the modern world is itself an extraordinarily rich story. But the key point for the purposes of Earth's story is this. In a geological eye blink, the descendants of those small, nocturnal, tree-dwelling mammals that had survived the asteroid impact 66 million years ago had gone from stone tools and campfires to cities and writing and organized agriculture. The pace of change was accelerating in a way that had no precedent in the biological world. And then, about 250 years ago, it accelerated again, dramatically. The Industrial Revolution, beginning in Britain in the late 18th century and spreading rapidly across the world, transformed human civilization in ways that were unprecedented for all of human history up to that point. The primary energy sources available to human societies were the muscles of humans and animals. The wind, moving water, and wood. All of these are forms of solar energy captured in real time. The Industrial Revolution introduced something categorically different. The burning of fossil fuels. Coal, oil, and natural gas are the compressed, chemically transformed remains of living things that died hundreds of millions of years ago. Their biological energy stored in chemical form over geological timescales. By burning them, human civilization was accessing an energy source of almost incomprehensible density and abundance. The consequences were staggering. Machines powered by steam engines could do the work of hundreds of human laborers. Factories could produce goods in quantities and at speeds that cottage industries could never match. Transportation was revolutionized, first by steam-powered ships and trains, then by internal combustion engines in cars and trucks and airplanes. Communication was revolutionized. The telegraph, telephone, radio, television, and eventually the internet collapsed the time and space of information transmission to essentially nothing. Agricultural productivity was transformed by mechanization, synthetic fertilizers, and the selective development of crops. And medicine was transformed by the understanding of germ theory, the development of antibiotics, vaccines, surgical techniques, and the whole apparatus of modern healthcare, reducing mortality from infectious disease, from injury, from childbirth, from childhood illness, in ways that dramatically extended the average human lifespan and allowed populations to grow as never before. The effect on human population numbers was unlike anything in the biological record. The global population first reached 1 billion people in 1804, which itself represents the accumulated growth of our species over hundreds of thousands of years. But the pace then began to accelerate sharply. By 1927, just 123 years later, there were 2 billion people on Earth. The third billion arrived in 33 years. The fourth billion in 14 years. Since the 1960s, the global population has continued to grow rapidly, reaching 5 billion in 1987, 6 billion in 1999, 7 billion in 2011, and more than 8 billion today. 8 billion people, the product of 4.5 billion years of planetary and biological history, now occupying every continent, every climate zone, every ecosystem on Earth. And here is where Earth's story becomes a story that is not just about the past, but about choices being made right now. Because the same forces that drove the extraordinary growth of human civilization over the past 250 years, the burning of fossil fuels, the industrial transformation of agriculture, the exploitation of natural resources at scales never before attempted, have had consequences that the geological record will mark as clearly as it marks any of the other major turning points in Earth's history. The burning of fossil fuels releases carbon dioxide and methane, greenhouse gases that trap heat in the atmosphere. Since the beginning of the Industrial Revolution, The concentration of carbon dioxide in Earth's atmosphere has risen from about 280 parts per million to more than 420 parts per million today, a level higher than at any point in the past 800,000 years. Global average temperatures have risen by more than 1 degree Celsius since pre-industrial times, with the rate of warming accelerating. Sea levels are rising as ice sheets lose mass and as the thermal expansion of warming ocean water pushes sea levels higher. The frequency and intensity of extreme weather events, hurricanes, floods, droughts, wildfires, is increasing in ways consistent with what climate models predicted decades ago. And beyond the direct climate effects, the human transformation of Earth's ecosystems has produced biodiversity losses that some researchers describe as meeting the threshold of a sixth mass extinction event, comparable in magnitude, if not yet in total losses, to the 5 great mass extinctions of the geological past. Habitat destruction, overexploitation, pollution, invasive species, and the direct impacts of climate change are driving species to extinction at rates far above the background extinction rate that characterized most of Earth's history. Coral reefs, some of the most biodiverse ecosystems on the planet, are bleaching and dying as ocean temperatures rise. Rainforests, which contain a disproportionate share of Earth's terrestrial biodiversity, are being cleared at rates that represent a significant fraction of Earth's biological heritage being lost permanently every year. This is where the long view of Earth's history is both humbling and clarifying, because the history we have spent this entire video walking through tells us several things simultaneously. It tells us that Earth has survived far worse than anything humans have done to it. The Great Dying killed 96% of marine life. The asteroid impact killed the dinosaurs. Snowball Earth froze the planet solid. And every time, life recovered. Given millions of years, the planet rebuilt. New ecosystems arose from the ruins of old ones. Biodiversity returned. The planet did not care, cannot care, will not care what happens to the creatures living on it at any given moment. It will survive us, whatever we do, that is certain. But it also tells us something else. It tells us how extraordinarily rare and precious this moment is. The confluence of factors that had to fall into place to produce a planet with liquid water, a stable orbit, a large moon stabilizing its axial tilt, a magnetic field protecting its atmosphere, the right chemistry, the right distance from a stable star. All of this, happening together over 4.5 billion years, producing a world of extraordinary biological richness and diversity. Life appeared here, survived here, diversified here, and produced thinking creatures capable of looking back at the full sweep of their planet's history and understanding what they see. That is not guaranteed to be common in the universe. It may be extraordinarily rare, and the biological heritage that this planet has accumulated over 3.7 billion years of continuous life, that heritage is not guaranteed to be recoverable on any human timescale if we destroy it now. The story of Earth is a story of constant change and constant adaptation. Every living thing on this planet is the product of an unbroken chain of survival stretching back nearly 4 billion years. Every mass extinction event reshaped the world and produced the conditions for new forms of life to emerge. Every catastrophe was followed by a recovery. But recoveries take millions of years. The creatures that went extinct in the Great Dying did not come back. The dinosaurs did not come back. What came after was different, sometimes better in some ways, but different in ways that can only be described as different, not better or worse. The planet recovered, but it recovered as a changed planet. The biological heritage of every extinction event is gone permanently. It can never be recovered. And that is true of whatever heritage we lose in the present moment as well. We are standing at a moment in Earth's history that is without precedent. Not because the planet has never experienced change, it has experienced far more dramatic change than anything happening right now, but because for the first time in 4.5 billion years, there is a species on this planet that understands what is happening, that can read the geological record and understand the mass extinctions of the past, that can measure the chemistry of the atmosphere and understand what it means, that can model the climate and predict what comes next if current trajectories continue, and that has the technological capacity to choose a different path. We are, as far as we know, the first species in the history of this planet, possibly the first species in the history of the universe, with the ability to consciously choose its relationship to the planetary systems that support it. The story of Earth does not end here. It will not end for another several billion years, until the sun expands into a red giant and eventually consumes the inner planets of the solar system. Whatever happens to human civilization over the next century or millennium, the planet will continue. Life will continue in some form, almost certainly. The question is what form? The question is whether the extraordinary complexity and diversity of life that has developed on this planet over 3.7 billion years, this biological heritage, accumulated through mass extinctions and recoveries and evolutionary explosions, and the patient work of billions of generations of living things, whether that heritage continues to exist and diversify, or whether it enters another bottleneck, another great dying, produced this time not by an asteroid or a volcanic eruption, but by the choices made by the species that understood the most about Earth's history and had the most power to shape its future. That is the question that Earth's 4.5 billion year story leaves us with. Not a comfortable conclusion, but an honest one. We know what this planet has been through. We know what it has survived. We know what was lost in each great extinction and what was gained in each great recovery. We know that we are living in a moment that the geological record will mark as clearly as any other transition in Earth's long history. The only thing we do not know yet is what we will do about it. That chapter is still being written, and for the first time in 4.5 billion years, the creatures writing it know exactly what they are doing. What happens next is up to us. Let us go back and spend more time with the age of dinosaurs, because a cursory mention simply does not do justice to what was one of the most extraordinary chapters in the history of life on this planet. When we left off, the dinosaurs had just emerged from the wreckage of the Great Dying, and were beginning their slow takeover of the Triassic world. But to truly understand what 150 million years of dinosaur dominance actually looked like, you have to understand the world they lived in, because it was radically different from the world we know today, and not just because the animals were different. For much of the age of dinosaurs, the climate of Earth was significantly warmer than it is today. There were no permanent polar ice caps for much of the Mesozoic era. The poles were cold and dark for half the year, as they are today, but not cold enough to support the massive ice sheets that now cover Antarctica and Greenland. Sea levels were dramatically higher than today as a consequence. The shallow interior seas that covered much of what is now North America and Europe were not geological anomalies. They were the normal state of affairs on a warm, ice-free planet. The atmosphere contained higher concentrations of carbon dioxide than it does today, contributing to a greenhouse effect that kept global temperatures elevated, and the land surface of the planet, as the Triassic gave way to the Jurassic and then the Cretaceous, was slowly being rearranged by the ongoing breakup of Pangaea into something that would begin to resemble, very distantly, the continental arrangement we know today. The breakup of Pangaea during the Mesozoic era had profound consequences for the evolution of dinosaurs and every other form of life on land. As the continents separated from one another and ocean basins opened between them, populations of animals that had previously been able to move freely across the connected landmass became isolated, separated by growing ocean barriers. Those isolated populations evolved independently, producing different species on different continents from common ancestors. This is why the dinosaurs of North America were different from the dinosaurs of Asia, and both were different from the dinosaurs of the southern continents. The breakup of Pangaea was an engine of evolutionary diversification, multiplying the variety of life by creating isolated evolutionary laboratories across the globe. The Jurassic period, roughly 201 to 145 million years ago, is probably the era most people picture when they think of the classic dinosaur age. And for good reason. The Jurassic saw some of the largest animals that have ever walked on land. The sauropods, those iconic long-necked, long-tailed, pillar-legged giants, reached their maximum size and diversity during the Jurassic. Brachiosaurus, Diplodocus, Apatosaurus, Brontosaurus. These names are almost as familiar as household words, and the reality behind them is if anything more impressive than the mythology. Diplodocus, for example, could reach lengths of over 25 meters from nose to tail. Brachiosaurus stood so tall at the shoulder that it could hold its head at the height of a 4-story building. And these were not rare, unusual creatures that squeaked through existence in small numbers. They were abundant. The Jurassic forests and floodplains of what is now western North America were grazed by herds of these giants the way the African savanna is grazed by elephants today, but scaled up to a degree that beggars the imagination. Sharing that Jurassic world with the giant sauropods were the first of a group that would eventually become one of the most successful and diverse lineages in the history of life on Earth. By the late Jurassic period, the theropod dinosaurs, the bipedal predators, had given rise to a group of small, feathered dinosaurs that were acquiring an increasingly familiar profile: wings, the ability to generate lift, True flight. The evolution of birds from theropod dinosaurs is now as well documented in the fossil record as almost any other major evolutionary transition. Archaeopteryx, the famous transitional fossil first discovered in Germany in 1861, shows an animal that is simultaneously unmistakably dinosaurian, with teeth, clawed wings, a long bony tail, and unmistakably bird-like. It had feathers, it could probably fly, or at least glide. It represents the moment in Earth's history when the dinosaurs that would ultimately outlast all their relatives by surviving the asteroid impact first appeared. When you see a bird sitting on a branch outside your window, you are looking at a living dinosaur, a highly modified, secondarily flightless to flighted, warm-blooded, sophisticated dinosaur. But a dinosaur nonetheless. The Cretaceous period, 145 to 66 million years ago, saw the final and in many ways most dramatic chapter of the dinosaur age. The continents had separated further, creating the diverse biogeographic provinces that would produce the greatest dinosaur diversity the planet has ever known. And in the Cretaceous, something else happened that transformed the world in a way even the dinosaurs could not ignore. Flowering plants appeared. The angiosperms, the group that today includes virtually every plant you can think of, from grasses to oak trees to every fruit and vegetable you have ever eaten, evolved and diversified during the Cretaceous, spreading across the continents and dramatically changing the ecosystems they colonized. Before the angiosperms, the dominant plants were ferns, cycads, and conifers. The Cretaceous world began with those ancient plant forms and ended with something that was well on its way to looking, in its botanical character, much more like the world we know today. The flowers that bloomed in the Cretaceous were primitive compared to modern flowers, but they were real flowers. And with the flowers came insects, the pollinators, diversifying in step with the plants they depended on. The co-evolution of flowering plants and insects is one of the great evolutionary partnerships in the history of life, and it began in the shadow of the dinosaurs. Now let us also give proper attention to what the oceans looked like during the age of dinosaurs, because the marine world of the Mesozoic was no less extraordinary than the land world. The seas of the Jurassic and Cretaceous were not ruled by dinosaurs. The great marine reptiles of the Mesozoic were not dinosaurs, though they evolved from the same ancestral group. The plesiosaurs, long-necked, four-flippered marine reptiles that ranged from relatively small, fast hunters to enormous filter feeders, were among the most successful marine predators of the Jurassic and Cretaceous. The largest plesiosaurs, like Elasmosaurus, had necks so long they accounted for more than half the animal's total length. The mosasaurs, marine lizards that evolved from land-dwelling ancestors and became secondarily fully aquatic, dominated the shallow seas of the late Cretaceous, with some species reaching lengths of 17 meters. The ichthyosaurs, dolphin-shaped reptiles that were so well adapted to marine life that they gave birth to live young in the water, swam the early Mesozoic seas in large numbers before declining in the Cretaceous. And alongside all these marine reptiles swam fish, sharks, rays, ammonites, the coiled-shelled cephalopods that were among the most abundant marine creatures of the Mesozoic, and countless other invertebrates that formed the base of the ocean food chains. The Mesozoic ocean was as rich and diverse and strange as the Mesozoic land. And then the asteroid ended all of it, or almost all of it. Mosasaurs, gone. Non-avian plesiosaurs, gone. Pterosaurs, the flying reptiles that had ruled the skies alongside the birds throughout the Mesozoic, gone. The ammonites, gone. After more than 300 million years of abundant existence. The impact and its aftermath eliminated not just the non-avian dinosaurs but a whole suite of other large, dominant animals across the planet. What survived was, by Mesozoic standards, the leftovers. The small things, the hidden things, the things that needed least to survive. And from those leftovers, in the Paleogean period that followed, the modern world was built. We talked earlier about the rapid diversification of mammals after the extinction event, but let us linger on that for a moment and really appreciate what happened. Within roughly 10 million years of the asteroid impact, a geological eye blink, the empty planet began to fill in ways that would have seemed unimaginable to any observer of the late Cretaceous world. The size range of mammals expanded dramatically as the pressure of large dinosaurian predators was suddenly lifted. Where the largest Cretaceous mammals had been the size of a badger, by the early Paleogene mammals were evolving into forms that rivaled the extinct dinosaurs in sheer bulk. Within 20 million years of the extinction, there were mammals as large as modern rhinoceroses. Within 30 million years, some of the largest land mammals that would ever exist were walking the land, Parasaurolotherium, a relative of modern rhinoceroses, stood nearly 5 meters at the shoulder and may have weighed as much as 20 tons, making it one of the largest land mammals in Earth's entire history. The oceans filled in equally dramatically. The whale lineage, descended from a group of land-dwelling, hoofed mammals that look superficially like large dogs, began returning to the ocean around 50 million years ago. The early stages of this transition are beautifully documented in the fossil record. Pachycetus, the earliest known ancestor of whales, was a fully terrestrial animal that spent time near water. Ambulocetus, a slightly later form, could walk on land but was also adapted for swimming. Rhodhocetus had reduced hind limbs and was primarily aquatic, but could still haul itself onto land with difficulty. Basilosaurus, from about 40 million years ago, was fully aquatic, streamlined, and recognizably a whale in its general form, though with vestigial hind limbs that it could no longer use for walking. By 35 to 30 million years ago, the ancestors of modern baleen and toothed whales had appeared, and the transition was essentially complete. The largest animals that have ever lived on Earth, the great whales, including the blue whale, the largest animal in the history of the planet, are the ultimate product of that journey from land to sea that began in the shadow of the early Paleogene forests. Meanwhile, in those forests, the primate lineage was developing along its own trajectory. We have already traced the path from early primates to bipedal Australopithecines to the genus Homo, but there is a part of early human history that deserves more attention. The period from the emergence of Homo to the emergence of modern Homo sapiens, a span of roughly 2.5 million years during which our lineage went through a series of evolutionary changes that cumulatively transformed us from clever bipedal apes into something categorically different from any animal that had ever existed on Earth before. The key development, the one that more than any other single factor distinguishes humans from all other animals, is the human brain. The average chimpanzee brain, our closest living relative, sharing roughly 98.7% of our DNA, has a volume of about 400 cubic centimeters. The brain of Homo habilis, the earliest member of our genus, was about 600 cubic centimeters. The brain of Homo erectus, which emerged around 1.9 million years ago and is the ancestor of all later human species, was between 850 and 1100 cubic centimeters depending on the individual and the time period. And the brain of modern Homo sapiens averages about 1,350 cubic centimeters. That is more than 3 times the volume of a chimpanzee brain, in an animal that is only slightly larger in total body size. The human brain, relative to our body size, is approximately 6 times larger than it would be predicted to be in a primate of our size following the normal scaling relationships between brain and body. It is by far the largest brain relative to body size of any animal in Earth's history. And that extraordinary organ, that 3-pound universe enclosed in our skulls, is what made possible every single development in human history from the first stone tool to the smartphone. The question of why the human brain grew as large and as rapidly as it did is one of the most fascinating unsolved problems in evolutionary biology. The leading hypothesis involves a feedback loop between increasingly complex social environments and the cognitive demands of navigating them. Smarter individuals were more successful in complex social groups. More successful individuals had more offspring, and so the brain kept growing. But whatever the exact mechanism, the result is the most cognitively complex object in the known universe. You are carrying one in your head right now, and almost everything that makes our species remarkable flows from that fact. Homo erectus, the species that emerged from Africa around 1.9 million years ago and spread across Africa, the Middle East, and Asia, deserves more attention than it usually gets in discussions of human evolution. It survived for an extraordinary 1.5 million years, far longer than modern Homo sapiens has yet existed. It developed more sophisticated stone tools than its predecessors, the Acheulean hand axe, a beautifully symmetrical, teardrop-shaped tool that required significant cognitive planning to produce and represents the first evidence of what looks like genuine aesthetic sensibility in stone tool manufacture. It controlled fire, as the evidence from sites like Wonderwork Cave in South Africa and Zucudian in China suggests. It built shelters. It lived in complex social groups. It crossed open water at some point, reaching the island of Flores in Indonesia by at least 800, an achievement that required some form of watercraft, or at minimum materials bound together to float across a body of water that was never a land bridge even during periods of low sea level. Homo erectus was not a primitive brute. It was a capable, adaptable, genuinely intelligent animal that made a significant mark on the world long before modern humans arrived on the scene. And it is also likely Homo erectus that produced in different populations on different continents the various human species that modern Homo sapiens would eventually encounter when it expanded out of Africa. Neanderthals in Europe, Denisovans in Asia, possibly others whose fossils we have not yet found. These were not simple, brutish cave people. Neanderthals buried their dead, sometimes with apparent ritual. They created ornaments. They used pigments, possibly for body decoration. They had brains as large as or larger than those of modern Homo sapiens. They were, by any reasonable standard, people. Different from us in significant ways, but people, and the fact that their DNA persists in the genomes of modern humans outside Africa tells us that when our ancestors met them, the recognition was mutual enough for reproduction to occur. The borders between human species, it turns out, were permeable. We are not a pure lineage descended from a single ancestral population. We are the product of encounters and mergers across the entire range of the human world, and the diversity that resulted from those encounters is literally written into our DNA. The development of fully modern human culture after the cognitive revolution of roughly 70,000 years ago was not a uniform, steady process across the planet. It was messy, non-linear, varied enormously by region and time period, and often involved apparent regressions as much as advances. But the overall trajectory was unmistakable. Over thousands of years, the complexity of human technology, social organization, and cultural production increased in a way that had no parallel in the biological world. By the time agriculture appeared 10,000 years ago, the pace of change had already dramatically exceeded anything that biological evolution could keep up with. The advantage of culture over biology as a means of adaptation is that it can change in a single generation. You do not have to wait for favorable mutations to spread through a population over thousands of years. You simply teach the next generation what you have learned. And with agriculture, with cities, with writing, the pace of cultural transmission and accumulation accelerated to the point where it became self-reinforcing in a way that made the progress of the previous hundreds of thousands of years look glacial by comparison. Every 10,000 years of human agricultural civilization produced more change in the human world than the previous million years of human existence had produced. Every 1,000 years produced more change than the previous 10,000. Every 100 years after the Industrial Revolution produced more change than the previous 1,000. We are now at the point where significant technological and social change occurs within a single human lifetime, within a single decade in some cases. The rate of change in human civilization has become so rapid that it constitutes a genuine discontinuity in the history of life on Earth. No other species has ever changed its relationship to the environment so rapidly, so comprehensively, and with such profound consequences for every other species sharing the planet. This acceleration of change is both the source of the extraordinary achievements of human civilization, the medicine and science and engineering and art and all the rest, and the source of the existential risks that now face both human civilization and the broader biological community of Earth. We are living in a moment that is, by the standards of Earth's 4.5 billion year history, absolutely unique. A species has arisen that understands to a significant degree the history of the planet it lives on, that can read the geological record and understand what it means, that knows about the Great Dying and the asteroid impact and the snowball Earth glaciations and the Cambrian explosion, that can look at the atmosphere and understand what the rising levels of greenhouse gases mean for the future. And that has the technological capability, if it chooses to use it, to change course. Whether it does is the most consequential question in the history of life on Earth. Not because the planet needs our help to survive. It does not and never has. But because the biological heritage of 3.7 billion years of life, the extraordinary diversity of species and ecosystems that Earth has accumulated through all the catastrophes and recoveries of its long history, is in a real and measurable sense at risk from what we are doing to it now. And because the civilization we have built, this extraordinary, improbable thing, this collection of knowledge and art and science and accumulated human experience going back 10,000 years, is itself vulnerable to the instabilities we are introducing into the planetary systems that support it. We started this story with a cloud of gas and dust in the darkness of space. We are ending it here, with you, listening to these words, 8 billion members of a single species on a single planet, in a single solar system, in one of hundreds of billions of galaxies in a universe so vast, it makes even the 4.5 billion year history of our planet look like a footnote. The chance that this planet exists, that it developed life, that life survived to produce complex animals, that those animals produced intelligence, that intelligence produced you. The sheer improbability of the chain of events that leads from that original cloud of interstellar gas to this exact moment is beyond any reasonable calculation. And yet here you are, the inheritor of 4.5 billion years of Earth's history, the descendant of every form of life that ever found a way through every catastrophe this planet could throw at it. The product of the greatest survival story the universe has yet produced, as far as we know. What you do with that inheritance is entirely up to you.